So in class 69, we're looking a little bit more at the relationship between wavelength frequency and now wave speed. What we determined was when we multiply wavelength times frequency, the units we get are actually meters per second because wavelength has units of meters, frequency has units of 1 over seconds, which is also known as hertz. When you multiply those two, you get meters per second. So if you just multiply these two columns, you actually get the velocity of the wave. And notice how it's kind of a constant number. Now, if our data were perfect, which is of course never going to be, but if it were perfect, all of these values would be perfectly equal. In some classes, some groups got really, really, really good data where it was almost perfect. And that brings up an important concept. In any given medium, wave speed is constant. Okay. So the speed of a wave is dictated by the medium. All right. So it's a really important point. So what we have here is wave speed equals frequency times wavelength. All right. So maybe you want to write that down, write out the words, but that little lambda symbol is wavelength. All right. So let's check out this question. It's an old one from a little way back we saw, but we actually didn't do this part of it, finding the velocity, the speed of the wave. So let's see, we have an amplitude of 0.2 meters. So I'll write amp equals 0.2 meters. We're actually not going to use that, but write it down for now. The wavelength is 0.4 meters and the frequency is 10 hertz. And we are looking for the wave speed. So we have V equals F times lambda. V is our unknown. F is going to be 10 hertz. And lambda is going to be 0.4 meters, which gives us 4 meters per second. So the G string on a guitar has a frequency of 196 hertz and a wavelength of 1.24 meters. So let's jot that down. So the frequency is 196. All right, and the wavelength is 1.24 meters. Okay, what is the wave speed? V equals F lambda. V equals F is 196 hertz. Lambda is 1.24 meters, which that kind of makes sense. That's about the length of a guitar. That's about a little over 4 feet, I think. So that's equal to about 243 meters per second. So I gave you a big hint here, but sometimes you might not get this hint. So let's highlight this. It should say it. So it is important to note that the wave speed will not change as long as the guitar string's properties do not change. With that in mind, what would be the wavelength of a C note with a frequency of 256 hertz? So let's say it's the same string, okay? We're not changing the tension, we're not changing how thick the string is, anything like that. It's the same string. So we know within any given medium, the wave speed won't change. So the wave speed is still going to be 243 meters per second, as it was in the previous one. We're looking for the wavelength, and we have a frequency of 256 hertz. Now, why don't you make a prediction for a second? You know that the frequency is going to be higher, right? So if the frequency went up from 196 to 256, what's going to happen to the wavelength? It's going to get bigger or smaller, right? Think about the relationship between wavelength and frequency. So let's see, V equals F lambda. V is 243 meters per second. F is 256 hertz. And lambdas are unknown. Divide both sides by 256, and you get 0.95 meters is our wavelength. And it says, does this answer make sense? Why? Yeah, think about the relationship between frequency and wavelength. Frequency went up from 196 to 256, therefore the wavelength had to go down. All right, which it did from 1.24 to 0.95.